how do KCNT1 mutations result in intellectual disability? There's a bunch of reasons for thinking that seizures are not the only problem with KCNT1 mutations. Particularly, there are conditions such as AD and LFE, or autosomal dominant frontal lobe epilepsy, where the intellectual disability is evident even before there are any seizures. And there are other mutations that can produce very similar patterns of seizures without the severe intellectual disability. So something else must be happening with the channels that we call SLAC. That was named by Bill Joyner, a graduate student in my lab who first found this was a channel. We found that these channels bind some very interesting proteins. These are proteins that regulate translation of messenger RNAs, particularly a protein called FMRP, the Fragile X mental retardation protein, and CYFIP1, the cytoplasmic FMRP interacting protein 1. In fact, you can immunoprecipitate these channels with messenger RNAs that are bound to FMRP. So what we've learned lately is that, in fact, as the channel gates open and close, as you stimulate a neuron and the channel becomes open, that actually triggers the synthesis of new proteins. For learning and memory, triggering the synthesis of new proteins is absolutely essential, and it has to be regulated. It can't be going on all the time. It has to be only the channels become active and then shut down afterwards. So what we have found is that under normal conditions, when you have the channel inactive, these two regulators, CYFIP1 and FMRP, they are normally sitting on the initiation complex of for translation of proteins. They bind to a protein called EIF4E, the initiation factor 4E, and when they're bound, they prevent the initiation of translation of messenger RNAs that are bound to this complex. When you stimulate these channels, we can do this a number of different ways, there is a translocation of these two regulators of translation away from the initiation complex to the channel itself. So now these bind more tightly, the channel is active, and in fact, FMRP itself stimulates the activity of the channel, so the channel becomes even more active during neuronal firing. But this results in the loss of these two inhibitors of translation at the initiation complex and triggers the synthesis of new proteins. We don't yet know the full extent of proteins that are stimulated, but we know actin is one of them, and sodium channels, particularly NAV1.6. The synthesis of sodium channels is very much stimulated when you activate the SLAC channels. We think it's a regulatory mechanism for ensuring that potassium channel and sodium channel expression levels are balanced. So we have studied a gain of function, that 474R474H mutation, and we have a mouse model of that. And we've compared what happens with the normal channel with this gain of function mutation. And what we find is that both FMRP and CYFIP are constitutively bound to the channel. There's very much less CYFIP1 and FMRP on the initiation complex. And we've also measured the rate of translation of actin and other proteins in the wild-type case and the gain-of-function mutation case. And in the wild-type case, when you stimulate the neuron, you stimulate translation. In the mutant case, this translation is already being stimulated. There's a constitutive increase in the translation of the sodium channels and actin and almost certainly other proteins. When you activate these further, when you stimulate them in a neuron, you can get a slight further translocation, but it's much smaller than what you see here. So we think this is actually a key element of the intellectual disability, because it is a serious disruption of the activity-dependent translation that's absolutely required for learning and memory. So the next part of this is, can this be fixed with pharmacological agents or other approaches? So we have used antisense oligonucleotides. Antisense oligonucleotides have already appeared in 2 patients, and they appear to have controlled seizures quite well. But we're now doing this on mouse neurons. And what the technique I'm showing you here is called, it's called proximity ligation assays. This is a technique where you use 2 antibodies that will only give you a signal when they are in very, very close apposition. That's to say, the molecules, again, the antibodies have to be touching. And if we look at the FMRP and SLAC interaction, we can see that under normal conditions, there's a lot of interaction of SLAC with FMRP. But surprise, surprise, if you actually get rid of SLAC using antisense oligonucleotide against SLAC, you have no more interactions of FMRP with SLAC. But look what happens then with the interactions of EIF4E with FMRP. That's the initiation translation complex with FMRP. That is lower to start off with. But when you get rid of SLAC, FMRP moves back to the initiation complex, and that would suppress the translation of messenger RNAs. The same thing happens for the CyPIP1, the cytoplasmic FMRP interacting protein 1, and the initiation complex. Now, when you get rid of SLAC, you suppress SLAC, you get a marked increase in activity of interaction between the initiation complex and this inhibitor of translation. So we can see this on Western blots. We can see this by this proximity ligation assay, and we can also see it in the proteins that are being regulated by SLAC. So I mentioned that NAV1.6, a sodium channel, its synthesis is stimulated when you activate potassium channels. This is the wild type. This is the mutant band here, where you can see there's much more NAV1.6 in the mice that express the mutation. But when we treat with the antisense oligonucleotide, the levels come back to control levels. So this gives us real hope that when you actually treat with agents, be they pharmacological agents that inhibit SLAC activity or antisense oligonucleotides that actually get rid of SLAC, that you may be able to restore the balance of these regulators of translation away from the mutant channels back to the initiation complex. And hopefully that will help to improve the intellectual functioning, improve learning and memory. That's the big hope. And that's my final slide.
So I have a question for Len. So I really like your model at Fragile X protein involved. So the question I have is, have you looked into the synaptic proteins, which is well known in the Fragile X disease, mass imbalance of translation of synaptic proteins? So have you looked in your model?
A translation of proteins. Yes, so like Fragile X, it appears to be select to a subset of messenger RNAs. So if we do a puromycin incorporation assay for total protein synthesis, that's not changed. But if we look at very specific substrates like NAV1.6 or actin, and there's a bunch of others we're looking at, those are changed. Interestingly enough, when we do the proteomics, the major things that change are mitochondrial proteins, and we're still looking for what the link is between those inner mitochondrial membrane proteins and SLAC channel activity.
Hi, Len.
Hi, Larry. How are you?
Hey, how are you? I don't have a good sense of what, in your model, what the phenotypes are going to be for a gain of function mutation or a loss of function mutation.
The gain of function of mutation is you're going to have excess protein translation, which is what you get with FMR, Fragile X, and a bunch of other disorders of intellectual disability. We don't know if there are any humans that have no SLAC channel activity. At least I don't know if there are any that have loss of both alleles. But the mice that don't have either. They don't have seizures, but they have no LTP when they're young, no LTD when they're young. They regain some LTP. These are long-term potentiation of synaptic responses. So these are things that are commonly used for assays of counterparts of learning and memory. So my guess is that the phenotype of the total loss would be very different. And that actually is something you would want to avoid with antisense oligonucleotides. You don't want to get rid of the whole thing. That, from what we know about mice, that would be a bad thing.